I'm very happy to introduce the speaker for this afternoon's first talk. And so in mathematics, we don't have much introduction, but I still want to mention that Costis, his famous work is on the game theory, and he received the Nevanina Prize at 2018. Today's talk is, I think, it's some connection of game theory with machine learning. So that's it. Thanks a lot. Thank you.
All right. Hi, everybody. Thanks for inviting me and coming to my talk. So I'm going to talk about deep learning, and in particular, how to train deep nets to think strategically, to make decisions that reflect some strategic thinking about the setting wherein these decisions are made. And the starting point for this talk is, of course, something we all know about, that deep learning has been having a lot of successes in the past decade or so that pertain to all sorts of different data modalities, like the ones you see here on the screen, and a lot of different problems related to those data modalities. Within this broader progress, there is an emergence of applications that are of the multi-agent type. And on this screen here, you see some examples of those. And I've categorized those into two groups, the top group and the bottom group. The top group are applications that are explicitly multi-agent, like playing difficult games like Go and poker, or interactions of many robots and things like that, self-driving cars with other self-driving cars or with humans. In the bottom, there are applications that are not explicitly, they're not born multi-agent. But for these applications, posing the problem as a game allows you to arrive at a learning outcome that you desire. And I'm going to talk about one of those. So in the bottom left, I'm going to talk a bit just to motivate a little bit the intricacies of the settings that arise in this kind of setting. I'm going to talk a little bit about the bottom left tile, generative adversarial networks. So a interesting and important challenge in machine learning is to generate synthetic data. Like the images you see here. So these images are not real humans. These guys never lived. These are synthetic data generated by some machine learning model. The type of machine learning model that generates this stuff is a deep neural net, of the type that Mike was talking about in the morning. Some deep net that takes as input boring randomness. So the most boring randomness is perhaps isotropic Gaussian noise, and processes. This randomness goes through all these linear and nonlinear and linear layers that Mike was talking about in the morning. And at the output, what you want is that you see some interesting sample. So you want to convert a boring sample to an interesting sample. So the goal of deep generative models is to convert simple randomness that is easy for us to sample to interesting randomness for which we don't have a parametric form. So, right, I mean, in this case, the distribution that is being targeted is the distribution of celebrity faces. The distribution over celebrity faces does not have a nice parametric form. All we have is access to samples from that distribution. So we have a lot of celebrities, in Hollywood or wherever, so we can take a headshot of those guys. And we have a large training sample from the target distribution of celebrities in this example. So what we want is a neural net that will take simple randomness and digest it into an output that looks like it's coming from that distribution. That's the goal of deep generative models. This task in itself is not multi-agent. It's I just want to function that maps boring samples to interesting samples. And there are many ways to come up with, to at least, attempt to, compute, to find such a function. A nice way to do it is what are called GANs, generative adversarial networks. And the approach here is to basically define a two-player zero-sum game whose equilibria will give you the function that you're looking for. So I'm going to describe a little bit how this looks like, just because it's interesting. So there are two players in this game. A player who has to set the parameters of the weights in the neural net architecture that you commit to some neural net architecture, and you want this pink player to set the weights on this neural net. You also have another player. That player is the discriminator player, and I'll tell you what he does. So the generator's goal is to set the parameters in a way that boring samples are converted to plausible samples for the target distribution, which in this case is celebrity faces. The discriminator is supposed to look at a sample that is either from the real distribution of celebrities, like these guys I hope you recognize. Okay, so Jennifer Aniston, Brad Pitt, right? So, okay. Samples from the real distribution or samples from the fake distribution, that the output of the generator. So the discriminator is supposed to judge which ones are real and which ones are fake. So you set up the utilities of this two-player zero-sum game in a way that you reward the discriminator to prefer real to fake, and you reward the generator to fool the discriminator. And this is the approach. The details don't matter, but let me just show you one way to define those utilities. That is nice. And these define what are called Wasserstein GANs. So in Wasserstein GANs, the utility of the discriminator, so the generator's utility is minus that. So the utility of the discriminator is a function of the parameters of the generator and the parameters of the discriminator. Sorry, omega became W here. I'm sorry about that. So the utility of the discriminator is the difference of two expectations. The first expectation is the output of the discriminator, the expected output of the discriminator when you plug in a real sample. The second expectation is the output of the discriminator if you plug in a fake sample. What's a fake sample? You sample the Gaussian and you pass it through the generator, and that gives you some sample. So you want to compare the expected output of the discriminator for a real sample and a fake sample. Right? So the discriminator is rewarded, the utility is high, if it outputs high on real samples on average and low on fake samples on average. The generator is rewarded to try to fool the generator. Of course, in practice, these expectations are approximated with finite samples and stuff like that, but that's not the point of my talk. So I'm just telling you the intention of how these things are defined. And that kind of makes sense, right? Because here's the intuition. If you fix the generator, the parameters of the generator, then you fix the distribution that it produces. That's the P fake indexed by theta. That's the output distribution of the generator. This is the real distribution. So if the architecture of the discriminator was rich enough to capture all one Lipschitz functions, then maximizing over W is basically selecting the best Lipschitz function to do the best possible discrimination job between the real distribution and the fake distribution. So basically, this would be the Wasserstein distance between the real distribution and the fake distribution, right? So given theta, the maximizing player, so the discriminator, is trying to compute the Wasserstein distance, at least if the architecture is rich enough. Therefore, the minimizing player is trying to minimize the Wasserstein distance between the distribution it generates and the target one. So this is roughly speaking how you do these things. Details don't really matter. What is important though is that you see here, there are neural nets involved, like I'm composing them and so on and so forth. So these functions are not nice. They're not going to be convex, they're not going to be concave. There's going to be a mess. Okay, so it's going to be a composition of two neural nets. So that's for motivation. So there's, again, coming back to my original thread, there's a ton of applications in this multi-agent front that are either explicitly multi-agent or implicitly, like where modeling as multi-agent is a useful tool. And there has been a lot of progress on the applied side of things. But there are some important caveats, which I wanted to discuss to motivate the rest of the talk. So what are some caveats? So one caveat is this, that if you don't pay attention to strategy and you naively train a model, it's just not going to be necessarily strategic. So here you see a Waymo car, this one with the camera on the roof. It's trying to enter into a highway, but it's been antagonized by human drivers, so much so that it has to abandon the attempt to enter the highway. It fails to enter the highway, exits the highway, and tries again. And if you've driven in San Francisco, this is a very common experience. Okay, there is a bottleneck, and surprise, surprise, at the top of this bottleneck, there is a Waymo car that is waiting for the best, the most opportune moment to make a turn or whatever. Okay, so training agents without taking into account incentives is not magically, right, like hitting it with gradient descent, is not naturally gonna create a strategic agent. In the same topic, but for LLMs, here's another example. So LLMs have been trained on a big corpus of data. This data contains all sorts of interesting information about the world, including games that people commonly play. So, in this corpus of data, there's a lot of instances of tic-tac-toe. Okay, so, and LLMs have learned the rules of tic-tac-toe. If you tell them, hey, I'm the X player, in this instance of tic-tac-toe, what should I do? They will, they'll understand, like what the rules of the game are, and will recommend you some action, right? So, but despite the simplicity of this game, they're not going to give you the right action. So the answer to this question that I made to ChatGPT is to go and play here, right? Which is obviously not the correct, the right recommendation, right? And I'm making this point because this is another instantiation where LLMs are trying to imitate the data on the internet. My point here is that by imitation learning, you're just not going to necessarily be strategic. You're imitating, but you're faking it, right? You're not strategically planning, even for these simple things. A priori, there's no reason to expect LLMs should be strategic. The posing of the training task for LLMs should not necessarily translate to being able to do strategic planning, except, like for other tasks, LLMs have a lot of what are called emergent properties. As it happens, there is no strategic emergent property, even for very simple things. That's caveat number one. Caveat number two is that if you train a neural net, again, without paying into attention about what may happen to it after, it can be manipulated. So the output of a neural net on this image is airliner. So what is this image? This image is this image, which is correctly recognized as pig, with the addition of a tiny bit of this well-orchestrated noise. This is not independent noise. It's well-orchestrated noise to manipulate the output of the neural nets. And these manipulations are very common. So this is a 3D printed turtle that some MIT students printed that is recognized as a rifle. And you don't even need to mess up with the painting, right? Like even rotating images can fool neural nets. The neural nets are very sensitive. If there is an attacker out there who's going to try to manipulate them, they're very sensitive. And that's caveat number two. Caveat number three is that like a legal system has analyzed a lot of interactions, right, and has come up with laws governing those interactions. But sort of like the basic premise in this analysis may fail to translate to when algorithms are interacting. So in this example, I'm going to show you some simulations by economists which pertain to a duopoly of two symmetric firms. So the two firms selling the exactly identical item. So in these kinds of scenarios, economics predicts that human control firms would converge to competitive prices. What this experiment I'm going to show you does is instead it says, suppose each firm runs its own reinforcement learning algorithm to update the price that they control, so the price for their good, given the history of prices that they have seen so far, right? So they have two independent RL agents trying to tune the prices of the two symmetric goods. And what happens is that you don't get the competitive price. In fact, you get something very close to the collusive price. So the RL agents are going to converge to some collusive behavior, which was not explicitly hardwired into the dynamics. These were just two firms, looking at the history and trying to, update their prices. But as it happens, so the emergent property here is that they learn a collusive price, and you can even inspect the dynamics and see how, if you were to push, for example, one of the two agents from the collusive price down to closer to the Nash price, to the competitive price, how the policies would react to that push so that they converge back to the collusive price. That's caveat number 3. So our assumptions about human agents fail when you have AI agents interacting. Fourth and more technical caveat is that the workhorse, the optimization workhorse of deep learning fails actually in multi-agent settings. So what is the optimization workhorse of deep learning? It is to pose a learning estimation problem as a minimization problem involving a non-convex function, and to try to minimize this function using a very simple algorithm that in particular only accesses the loss function with first order queries. Okay, so here we're operating in high dimensional spaces. There's not much, it's very expensive to compute Hessians and do, say, Newton. So typically people do gradient descent or some variant of gradient descent to solve these types of problems. And of course, non-convex functions are NP hard to optimize. But what you can show is that gradient descent will arrive at a local minimum. And in practice, these local minima are not too bad for applications. In fact, sometimes you prefer local minima to global minima because global minima may even overfit the data. So that's the single agent story. The single agent story is so successful that it has motivated frameworks, and these frameworks are algorithmic and software and hardware frameworks that are put together to open up this technology to the creative spirits of the whole world, right? So there's software and hardware optimizations that allow exactly someone to write down a neural net, get access, pay Amazon, get a lot of data, and train it with gradient descent. It's very easy to do. And like having such a framework is intricately related to the success of deep learning, because you don't need the expertise of it, of a domain expert to target a particular setting, right? You can be agnostic. Like typically, these architectures are quite agnostic about the underlying application. Yeah, but you can do trial and error, and we have arrived at a very rich ecosystem of trained agents. Okay, so it's important to have a framework for doing so. It has been so successful that there is some hubris out there, right? And this code is an example of that, right? That doesn't matter. You don't need to understand a domain. Scale is all you need. If you make your neural net, have 1 trillion parameters, eventually it will, figure things out. Okay, so this code is very common, but it's very misleading because scale is definitely not all you need. And like it's easy to break this by considering multi-agent settings. Okay, so this is my fourth caveat here. So if you have many agents in the same environment, and you ask every agent to update their own control variables using gradient descent, what happens is cyclic or chaotic behavior. This is a common experience in practice. And okay, just here's an example of that, like back to GANs. Here's two sort of like standard and possible behaviors with gradient descent dynamics in GANs. So here you have the discriminator and the generator running gradient descent to optimize their utility functions. It's a zero-sum game, so one guy is trying to maximize the utility, the other guy is trying to simultaneously minimize the same utility. And these are two common experiences that you may see. So here the target distribution are handwritten digits. And what happens here is that you have two phenomena. So one is mode collapse. So like this is what the generator generates if you were to stop this training process at different iterations t. As you see, at every checkpoint here, the generator has collapsed to a single mode. It doesn't create a diversity of symbols, and in fact, it's not even a handwritten digit from the digits we all recognize. It's some other digit that it came up with. Okay, that's mode collapse and on the wrong mode. Okay, over here you see the other type of behavior that's very common. So here, the target distribution is a mixture of Gaussians whose means are arranged around a cycle. And again, here, if you were to stop the training process after different t's, you see this, like rock, paper, scissors behavior that Mike was talking about, where, like the generator is generating from some mode, and then, the discriminator catches up with them, and then they move to another mode, and so on and so forth. So they chase each other around. Fourth caveat is gradient descent fails. Fifth caveat is game theory fails. Why does game theory fail? Of course, this interaction is a two-player game. More generally, if you have many robots interacting with each other or self-driving cars interacting with each other, you have a situation where you have, like n agents. These n agents are choosing some multidimensional parameter vectors and plug those into some complicated utility functions. What's complicated about the utility functions? They involve composing neural nets, like what we saw in GANs. So these utility functions are not concave. And this is enough to break game theory, right? So game theory likes when, likes modeling games in a way that the utility function of an agent is concave in their own decisions. Right? That makes best response is a unique thing, but you don't want to say utility that goes like this, right? Because then best responses could be isolated, like and they may not be like and they're not necessarily a convex set, and that breaks the existence theorems underlying the existence of Nash equilibria. Okay, which is what I'm writing here. So Nash equilibrium and other types of equilibria may not exist the moment you remove the concavity of the utilities. The other thing I'm noting here is that, typically in the multi-agent deep learning world, at least you have continuous utilities, because these are, neural nets composed with each other. So at least you get continuity of the utilities, and these are almost everywhere differentiable as well. That's one thing you may want to exploit. Okay, so now let me dive a little bit deeper into what I mean by Nash equilibrium failing, and also, like, I'm not sure how many of you are familiar with game-theoretic equilibrium concepts, so let me just be precise. So I'm just going to define three basic equilibrium concepts in one slide. The most basic one is Nash equilibrium. What is a Nash equilibrium for this complicated game? It's a selection for each of my agents, so that no agent I has an alternative selection that could improve their utility, right? If the other guys do what they do, no agent I can discover an alternative setting of their parameters to improve. That's Nash equilibrium. then you can define a randomized Nash equilibrium, also called mixed Nash equilibrium, which is rather than having each agent select a fixed setting of their parameters, you can have a distribution for a distribution over settings of parameters for each agent. And you want the same inequality to hold, but with an expectation outside. So you're sampling from the product measure of these distributions a setting of parameters, and you don't want there to exist a opportunity for agent I to improve their utility. That's mixed Nash or randomized Nash equilibrium. And there's a third one that I may use later in the talk if I get there, called cross-correlated equilibrium, where you even allow the P's to, that you allow joint setting, a distribution that correlates the actions chosen by the agents. Like one, basic example of what this thing is, for example, like a traffic light situation where like this distribution P is basically telling one agent green and the other agent red, or the other way around. It's a mix between red green and green red, right? So this is the type of thing, and like if you see your recommendation, you don't want you don't want to like an expectation, you want to follow that recommendation. All right, so what do we know about these notions, about their existence? Any questions about the setting or the notions themselves? All right, what do we know about these notions? So, well, an important result, coming back to the concavity assumption I was talking about earlier, is that if its UI is continuous and concave in Xi, so it's continuous, and it is concave in Xi for all settings of X minus I, right? So there's a comma there. And every set is convex and compact. There's the first kind of Nash equilibrium, and therefore there's this, the second kind as well, and the third kind, because these are just bigger sets of things, right? And already this result implies Nash's fundamental result in game theory. So Nash was considering not this setting, considering a simpler setting where every agent has a discrete set of actions and their Xi is a distribution over them. So for Nash, this Xi was the simplex whose corners are a discrete set of actions, and the UIs are the multilinear functions in this distributions Xi. Well, this theorem implies Nash's theorem. It's one of the most important things in game theory. Okay. Okay, but my point is that if you break the concavity assumption, Nash equilibria don't exist. And perhaps the most trivial example of that is this game here. This is a silly game. You have it's a two-player zero-sum game. Both agents choose a scalar. One guy is rewarded for distance squared. The other guy is penalized for distance squared. So this game, of course, has no Nash equilibrium of the first kind. Why? Because if they play the same thing, player one is unhappy, wants to go away. If they play different things, player two is unhappy, wants to go and match player one. So this game has no Nash equilibria. What broke? Well, the utility of player one is not concave in X1. The moment you break that, very simple cases, fail to have Nash equilibria. Generative adversarial network is just a more complex, example of that, right? And as I was saying earlier, you compose neural nets. The function is definitely not concave unless you're in a very simple setting. So it's not have Nash equilibria. And my point here is this: so you want to train a GAN. It has no Nash equilibria. What the heck are you exactly looking for? It's not clear what you're looking for. So that's part of the motivation of this talk. You can definitely set up this multi-agent environment where every agent is choosing parameters in a neural net. But if Nash equilibrium, if game theory fails, what exactly are you looking for? So people have not thought about it carefully. One common way to resurrect equilibria is to convexify the setting. And rather than considering Nash equilibria of this kind, consider Nash equilibria of the randomized kind. And if you're if these things are convex and compact, then this second kind exists. Okay, so if you're in if the UIs are continuous but not necessarily concave, if you allow yourself, if you allow, the generator to, set their parameters in a randomized way, and the discriminator to set their parameters in a randomized way, then you get a Nash equilibrium back. The problem from a practical point of view is that the support of P1 and P2 and etc. is going to be continuously, it's going to be continuous in general. It's not a practical suggestion. And finally, if the Xi's are non-compact, you lose this again. Okay, so if right without compactness, this is not true. You lose also the second kind of equilibria. And a nice example of that is the guess, what is called the guess the larger number game. It's a two-player zero-sum game. Both agents are supposed to choose a real number. Whoever picks the bigger one gains a point. Okay, this game has no Nash equilibria, or even mixed Nash equilibria. Why? Because if I know your support, I'll just make my distribution, whatever, dominate yours by a lot of probability. So I just choose something that dominates yours, and then you choose something that dominates mine, and we can just chase each other to infinity or whatever. All right, so these are my caveats. Okay, so this is the backdrop for this talk. Okay, so there are issues. Things don't extend easily to the multi-agent setting, and in my view, it's a problem because telescoping to the future, I do think that multi-agent applications are going to multiply. So we need some kind of understanding of the setting and some framework to address the challenges that will arise in this kind of setting. Here are some questions I want to ask here. Okay, so game theory breaks. What are meaningful then and practically attainable solutions in this setting? Second question is, why does gradient descent fail in this setting? Why if you have a multi-agent setting and you have each agent use gradient descent, why does this fail? And finally, is there a framework that is generic, that doesn't need you to know, to have domain expertise about the setting? Is there a generic framework for multi-agent deep learning? So the sub-question I want to ask for the first, towards answering the first question is like, in single-agent deep learning, because global optima are intractable, people have, are targeting local optima. Is there such a thing in the multi-agent world, like some local notion of equilibrium that is guaranteed to exist? So the second one is about, is there some underlying intractability? Or is it just the gradient descent is not the right notion in this setting? Yeah, and the last one is, can I get this generic setting, or do I need to have domain expertise about the application that I'm targeting? So these are some of the questions. Let's see how much of that we can address in this talk. Okay, so let me address the first kind. So again, in single agent setting, if you're optimizing over a compact set, convex compact set, there is a global optimum, but it's intractable. So you're targeting local optima. In the multi-agent world, we're a bit more complicated, right, situation. So global Nash equilibria don't exist. So the question you want to ask is, okay, can we, so that's not the right optimization target for multi-agent deep learning. Do there exist some local kind of Nash equilibria? So how do you define those? So let's look at our setting. Again, the setting is this. I will assume that the UIs are Lipschitz and smooth almost everywhere. In fact, I'll assume that they're smooth everywhere, that the gradient and are Lipschitz everywhere for simplicity. I'm also going to allow something that I didn't say earlier, but which may arise in practice. I'm going to allow constraints that tie together the actions of different players. So I'm going to allow, for example, if this guy is producing something and this guy is consuming something, of course, what this guy is consuming is constrained by what this guy is producing. So in general scenarios, Or like if my self-driving car goes this way, you cannot just go and like be on top of me, right? Like there are constraints imposed by each other's action, so I'm going to abstract them away by this script S there. But this is my overall setting I want to target, and I want to ask: is there a meaningful and practically attainable optimization target in this setting? What I mean by meaningful and practically attainable, this is just just words. How can I instantiate these words? So for meaningful, I want at least the following things. I want that it is guaranteed to exist. So I cannot just go and tell practitioners, try to find this if it doesn't exist. I want to guarantee existence. I also want it to be the case that it is easy for the players using the information that they have about their utility to verify that they are at equilibrium. So for example, if the agents only have gradient access to their utilities, I want them to be able to verify that they're at equilibrium using gradients of their utilities. I don't want them to compute Hessians or something higher order tensors. And practically attainable, I want some kind of, first order, second, some lightweight computational process that they can run distributedly to converge there. These are my desiderata for now. And my goal is to perhaps generalize to this setting the notion of local optima that have been so successful in single agent settings. So this is my. And a very, 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 very weak notion of local Nash equilibria I can define is this. I want a point, I want a setting for the parameters of every agent such that every player, given what the other guys are doing, is playing a local opt to their utility, as opposed to global opt to their utility, which was Nash equilibrium would like me to have there. So that's very natural. But except that local opt doesn't mean anything. So I have to be more precise about what local opt means. I mean, okay, like I guess there is the mathematical definition of local opt, but it's not computationally nice. So verifying that something's local opt is NP hard in general. So it has to be some easier notion of local opt. So, and there is a hierarchy of local optima. The babyest version of local opt is what is called first order local opt. What does that mean? It means that it is max as far as the first order Taylor expansion is concerned. This is typically, so in single agent deep learning, people typically target this kind or the second order kind. So they also, sometimes also want to guarantee something about the Hessian's eigenvalues at that point, but they're not going to verify high order tensors. Okay? So you want a baby version of local opt. You cannot just, if the Hessian is all zeros, you are not going to go to the third order tensor and fourth order tensor and, nth order tensor. So you want to do something computationally easy. So the babyest version you can define is the first order one. Okay? So let's play with that for now, and we'll consider second order later. So the simplest possible generalization of local optima from single agent setting is these things. So I want a strategy for every agent so that every agent plays a first order local optimum for their utility against the other guys. Okay, so let's look at it pictorially. Okay, so just to understand. So this, so for xi star to be a local first order local best response, it must satisfy one of these two properties. It's a first order concept, right? So, what does it mean to be first order local opt? Well, player I has to find themselves in one of these two scenarios. So this orange set is the constraints imposed to player I by the strategies of the other players. So this script S was the global constraints in my setting. By script I x star minus I mean, but by the way, sorry, I hope you are familiar with this minus I notation. Minus I means the strategies of everybody but I. It's a very useful one in game theory. So these are the strategies of everybody but player I. These strategies impose some constraints on player I. These are the constraints. For xi star to be a first order best response to what the other guys are doing, it better be that one of the two scenarios are true. either the gradient at xi star is 0, so first order information doesn't, first order information of my utility where I'm playing doesn't give me a direction of movement, or xi star is on the boundary and a gradient step would take me outside, so that if I project back to the set, I'll land where I started. So in either of these two cases, the gradient of my utility, where I'm currently playing, doesn't tell me where to move to improve my utility, and I declare victory. Okay, this is what first order local optimum means. I'm not saying it's a well-motivated notion. Perhaps, if my gradient is 0, perhaps I want to look at the Hessian. And if the Hessian is 0, perhaps I want to look at the third order tensor. So as I said earlier, there's a hierarchy of these things you can define. This is at the bottom layer of the hierarchy. And a compact way to write is, of course, this one, right? That for xi star to be a first order local opt, it must be that, like if I do a gradient step and I project back to the constraints, I land where I started. So it's a fixed point of basically gradient descent. Right? So I went a long, circuitous route to tell you that, like the babyest version of local opt you can define is is a fixed point of gradient descent. So this is what first order local Nash is. First order local Nash is a selection x1 star to xn star that is a fixed point of the gradient descent dynamics run by all the agents. Does it exist? Well, I mean, it's a fixed point, so it does exist. It's a fixed point. Okay, so you have to take care of the fact that, like these strategies appear in the set where you're projecting them, but you can iron these details. This thing exists. If the constraint set is convex and compact, first order local Nashes exist. What about second order local Nashes? Do those exist? These are better motivated compared to this. Do they exist? You guys already know the answer to this question about whether they exist or not. What is the answer? I gave you one example earlier in my talk showing that they don't exist. Right? So anybody remembers the example? So I gave you this game, right? So x1 squared minus x2 squared. It was a zero-sum game. So here the utilities are already quadratic. So doing second order Taylor expansion is not going to change anything. And I already argued that this thing does not have global Nash equilibria, but global and second order local are the same thing. And because it doesn't have global, it doesn't have second order global. So back to here, like this is really the only option I have in multi-agent settings. Any higher order thing is not going to exist. All right, so it does, at least this thing exists, not super well motivated, but it does exist. And ultimately, okay, it's a fixed point of gradient descent. This is what people are trying to run in these kinds of settings. And it's also verifiable with first order queries to your utilities. So it's reasonable. Second question, can you arrive? Like, is it possible to get there? Is it tractable? Can you get some lightweight process that gets there? Remember, practically speaking, despite the fact that this is defined as a fixed point of gradient descent, I already said that gradient descent suffers in these settings, right? It's cyclic or chaotic in these settings in practice. Is there an alternative that stabilizes those dynamics and converges to this kind of thing? So here the news are bad. Okay, so what you can show is that any method, any first order method, any method that accesses the utilities with gradient queries and value queries needs exponentially many steps to converge to such a thing, even to an approximate one. So finding an approximate Nash equilibrium, so a point that doesn't move too much with after one gradient step, you'll have to pay exponentially in the dimension or this epsilon, 1 over epsilon, to find it. You need to query the utilities exponentially many times to identify such a thing. So if the only access you have to your utilities is with gradient and value queries, you cannot get there. It's not a bag of gradient descent, in other words. Any first order method will take exponential time to get there. So what if you don't have just first order access, but you have higher order access? You still need super polynomial time. Even if you can see the details of the function, you don't just have query access to the gradient and the utility. You still need super polynomial time, unless some complexity-theoretic collapse takes place. Namely, unless a complexity class called PPED collapses to P. Okay, so what is this PPED? So you're familiar, I hope, with NP and NP completeness theory and the class P of polynomial time computable problems. So, so P contains, for example, linear programming, while traveling salesman is complete for the class NP, meaning that is among the hardest problems in the class NP by the way, NP doesn't mean non-polynomial, it means non-deterministic polynomial. Okay, so in case you're not super familiar. So PPED is a class that's between these two classes. And in particular, it's a class that characterizes exactly how hard it is to compute Brauer fixed points. So fixed points of Lipschitz functions, Nash equilibria in multi-agent general sum games, and many other problems in combinatorics or economics or problems related to fixed points. So what we show basically, like the result that I'm talking about today, is that in this multi-agent deep learning settings, even if you have two agents and the setting is zero sum, and even if your target is just local Nash, it's as hard as all these other problems. So it's as hard as this hard class. So now, okay, I guess, okay, so these are bad news. So I guess the plan for the next 10 minutes or so is to give you some intuition about why the heck this happens. Why is finding local optima hard in a multi-agent setting? And the other thing I want to tell you is like, okay, like these are bad news. Are there any good news? Like, how are we going to go about multi-agent deep learning? Okay. So let me first offer intuition about this result, and then I'll get to the possible proposals to get out of here. And for the intuition, I want to compare the two settings of interest here. So I want to do a comparison between single agent optimization settings. So I want to compare non-convex minimization, which is the same as non-concave maximization on one side. And on the other side, I want to compare two-player zero-sum games that are with non-concave utilities. And I want to understand why is it that over here we can find local optima with gradient descent, while what changes over here and we cannot, it is intractable to find them. And I want to convince you that there is a big difference between the two settings. So what I'm going to do, I'm going to plot here. So I'm considering, okay, like these are equivalent. Non-convex minimization, non-concave maximization are the same. So my example is going to be about non-convex minimization. So in my example over here, I have a player who's controlling both the x and the y variable. And what I'm showing you is a possible better response, improving path for the minimizing agent. And I'm tracking the objective value along this improving path. Well, improving paths means that the objective function improves, right? So the function values have to go down as the agent is trying to improve their objective, right? So in this case, the objective itself acts as a Lyapunov function, witnessing that something is improving as the agent is making changes to their decisions. And in fact, if I'm optimizing over a compact domain, there's going to be some absolute lower bound to my function. And if the steps that I'm making are greedy, so if I'm making not just infinitesimal steps, but I'm insisting that I'm only going to make a step if it's at least epsilon improving, then this thing has to end, right? So there is a global minimum of the objective in this compact set. I'm only making steps that improve by epsilon. At some point, I'm going to hit a target. And TLDR, this is the reason why gradient descent works in deep learning. Like the argument, so all proofs that gradient descent works in single agent deep learning are basically this, that, as the function value itself acts as a Lyapunov function witnessing that the gradient descent dynamics will eventually has to stop. Well, this is what's happening in the single agent front. On the multi-agent front, things are funky, right? So I'm going to plot again I'm going to consider again a zero-sum game, and I'm going to show you. And now I'm going to have the minimizing player move in the horizontal axis and the maximizing player move on the vertical axis, and I'm going to show you the utility of the minimizing player. So along horizontal moves, because the minimizing player is playing, my objective has to go down, because that for the minimizing player to make those moves, it has to be good for them. So the objective goes down. It's a zero-sum game, though, right? So all the vertical moves are good for the vertical player, for the max player. So they increase the objective value. So what you may see is, the function value, for example, doing this, or it could be this, right? And in particular, what is interesting here, which is very different from over here, is that you can see cycles in the best response, in the improving dynamics, right? You cannot see cycles over here, but you can see cycles over there. And the other thing that you see is that this possible repetition of values. And repetition of values is bad for optimization algorithms because, not only you're, expending effort to make the step, but it's not like you're gaining any, useful information that can guide you for, where to query the function next, right? I mean, like you see, like here, even okay, if you find yourself in a cycle, you're kind of screwed, right? Because if you were to follow the dynamics, at some point you'll find yourself where you started. But even if you start on a non-cyclic path, improving path, because of this repetition of values, you don't get a lot of insight about where to query next to identify a local Nash equilibrium, which would be an endpoint of this thing. Okay, so this is the intuition. Now, to turn this intuition into an actual proof, you would have to, what you want to do is you want to take, an example like that, and you want to basically, identify function f whose best response dynamics are an exponentially long, space filling like curve that hides as much information as it can from the algorithm, no matter where the algorithm queries, right? Because there's no constraint that I'm trying to prove a general query lower bound. There's no constraint that the algorithm is only going to query along a best response path, right? So as far as I know, the algorithm could do other weird things, right? It could query all over the place and use that information to where to query next, and so on and so forth, right? So, and I don't know. The truth is, I don't know how to do this deduction without appealing to other machinery that comes from complexity theory. I don't have a direct implementation of the scheme. I don't have a direct way to find a smooth function with a property that you're forced to make exponentially many queries to this function and its gradient for you to find a local Nash. I don't have a direct example. The only way I know how to do it is to go through all this PPD machinery I was mentioning before. And, like if you're interested, after my talk, I can tell you a little bit about this machinery. But this is basically why 2 players are too many. Okay. And what this means, right? So what this result means is that, right? So I guess I mentioned 2 results. I mentioned a query complexity lower bound, which is not a computational complexity lower bound. It's just an information theoretic lower bound, and a complexity lower bound, which says that you have to make super polynomial many queries, even if you can see the details of the function, unless this class collapses to this class. Okay, so I guess, at this point, it's not clear how to extend this success of deep learning to the multi-agent setting. Okay, so it's not clear how to define a generic framework that allows you to write a deep net for every agent, and recommends a particular optimization procedure that each agent can run to convert to something that is reasonable. Except, okay, so and now I want to, okay, that's negative, that's bad news, but let me end on a more positive note. There is some progress that you can make, and I'm excited about some aspects of this project. So let me tell you how I'm thinking about it right now. So first of all, like any complexity theoretic result, it's a worst case result, right? So what it says is that there exists a hard function that will force you to take exponential time or super polynomial time, even if you can see the details of the function. But it doesn't mean that practice might be better behaved. So perhaps despite that obstacle, you can hope. Okay, like people try to find SAT solvers and things like that, right? So SAT is an NP hard problem, but people still have produced nice SAT solvers. So perhaps you can go this way. So you can say, look, I don't care that it's intractable. Let me just try to come up with a nice method that I hope in practice converges at reasonable speed to the local Nash. And in fact, you can exploit the connection between, right? Like the connection of this problem to PPAD and fixed point problems that characterize the complexity of PPAD to come up with the dynamics that converges. So we have followed that approach, and we have created some dynamics that actually are guaranteed to exhibit asymptotic convergence to the local Nash. And here I'm showing you an example in very low dimension of how our algorithm works over here, asymptotically converging to the Nash, to the local Nash, in comparison to what would happen to the gradient descent versus gradient descent algorithm if run by these 2 players. These are 2 players, right? So one is controlling the X moves, the other is controlling the Y moves. So if they each run gradient descent dynamics, what happens is these are different initializations. So what you get into a limited, unless you start at the local Nash, in which case you stay there, all other initializations will eventually get you in this cycle. Whether you start inside or outside of this limiting cycle, this is what will happen to you. All right. So this is a typical behavior of, not a typical. It can be chaotic. It may not even get into an infinite cycle, but this is a very common behavior of gradient descent settings. This is what our dynamics does. The problem with our dynamics is it's second order. It looks at the second derivative of the utilities. And it's not as practical for this reason, right? Because here the goal is to operate with neural nets with 1 million parameters each. So the second order tensor is 1 million squared, which is not something I want to compute at every step of my iteration. So an interesting open question is to do a compromised version of our algorithm, which is not as exact, but only does first order computations. So that's one interesting open question coming out of this work. The second thing I want to mention, which is something I'm excited about these days, is this. Okay, so local Nashes exist, but they're intractable in general. Is there anything to gain by considering correlated equilibria? And like over here, the intuition is that like even in nice games, even in concave games, Nash equilibria are intractable, as I mentioned earlier, but correlated equilibria are tractable. So the question is like like if I replace global Nash with local Nash and global correlated with local correlated, can I actually get tractability over here in the multi-agent deep learning world? And in fact, this is the case. Okay, so you can define a notion of local correlated equilibrium that is tractable. And let me tell you my proposal here and what you can prove. So here's the proposal. Okay, so I'm skipping some projections because I want to make this slide super ugly. But rather than finding a single X star where everybody's gradient is 0 up to projections, I want to find a distribution over X stars. I want a joint assignment, a randomized joint assignment of parameters to all the neural nets, so that in expectation, the expected gradient of every player is 0. Right? So like in expectation over the recommendations, there's no consistent direction that any one neural net can push towards to try to improve their utility. So if this distribution has support 1, this is exactly the local Nash equilibrium concept I had before, because if P's support 1, then there's a single vector x1 star through xn star, and what I want is all the gradients to be 0, so that's a local Nash. Again, I'm skipping the projections because I don't want to make this ugly. So my question here is like, okay, like if I increase the support from 1, which is local Nash and it's intractable, to bigger than 1, is there any point at which actually this becomes tractable? And interestingly enough, this is the case, and you don't need to increase the support to be exponentially large. There is, you can prove that there is a support size that's polynomial in the dimensionality of the setting, such that this thing exists and is tractable using gradient descent. And I'm very optimistic that this could be a starting point for a general framework, because here I'm not using anything about the setting. I get existence, I get a reasonable solution concept, and it's tractable using gradient descent. So this is where I'm currently at. Okay, so I want to propose that a variant, this or a variant of this, is a good starting point for multi-agent deep learning. Okay, so and again, again, just to remind you, my thought process was global Nash don't exist, so we have to do some compromised notion of equilibrium. The natural one was local Nashes. Those did exist, but were intractable. So the next relaxation is to consider, rather than Nash, correlated equilibria, and ask, okay, like, do these become tractable? And it happened. So these are the good news for today's lecture. And this is pretty much it. I had an extra slide for global correlated equilibria, but I'm going to skip it in the interest of time. And thank you very much.
Machine learning, in particular, neural networks-based machine learning, was inspired by biology and neuroscience. And if you study how humans behave with these kind of problems, it doesn't look like they really follow Nash equilibrium logic. For example, Herbert Simon many years ago suggested that maybe what they're trying to do is following a satisfying.
Yeah, satisfying.
Maybe that's an even deeper modification of Nash equilibrium is actually the way to deal with multi-agent settings?
Yeah, so I mean, that is a great question, and it connects very well to what Mike was talking about in the morning about bounded rationality and, agents like humans not being that good, like Kahneman's work and so on and so forth. But I disagree. I don't disagree that humans are not good in strategy. I'm not an expert there, but over here we have a normative perspective, right? Like, I want my self-driving car to be able to change lanes, and it's not able to. I want my language model to recommend to me what to do in a strategic scenario, and it's not able to. I want my, my robot to play soccer against this other robot, or my drone to play whatever, drone soccer with the other drone of my opponent or whatever. The point here is that, in some scenarios, you don't want to just imitate humans who might be bad at making decisions. Maybe you genuinely want to get good agents. Maybe you want to beat humans in chess or poker or Go, or you are in a situation where your agent is going to buy your stock or whatever. You don't want to say, oh, I suck at investing. Okay, why don't I also get an agent that also sucks at investing, right? So the fact that I'm not good at something doesn't mean that my agent shouldn't be good at that. But if my agent is going to interact with humans, it is important to understand what rationality assumptions you're going to place on humans, right? Like, if my self-driving car is going to drive in a road full of human drivers, it's good to have the right assumptions about humans to be able to drive efficiently and not, get into these messy situations I was talking about before in San Francisco. So I guess there is a point of both. Okay, so it's important. Like, in some situations, I genuinely want a good agent, but in some other situations, I want to model my opponents, and those opponents could be humans with bounded rationality. So I may want to exploit them. I may want to behave in a way that is not going to be messy because I'm a place to make assumptions on these human agents and stuff like that. Yeah, but that's a great question, and it requires a lot of thinking. Yeah.
You talked about the GANs and how that falls into the two-player paradigm. So if you look at your correlated equilibrium, what would that imply in that setting? I mean, what does it mean?
Right. So that's the experiment I should have here, but I don't have. But yeah. So I think, so I'm excited about these new notions. Like, it's very recent work. And the next step is to try it in practice, like in a GAN situation or a robot soccer situation or some other multi-agent situation. But that's a great question. And it could be this variant, it could be some related, even tighter variant. So now I'm thinking about, this variant was coarse correlated equilibrium. I'm actually currently on the theory front trying to define a correlated equilibrium notion, which is going to be a bit stricter. So, but yeah, the next natural step is to try it in practice. Yeah.
Wanted to ask actually a couple questions about gradient descent. One, you showed a slide where there was a limit cycle that you ran into, and I was wondering what that was due to. Was that step size that causes the cycle? And normally gradient should end at a local minima, right?
It's a two-agent situation.
Yeah,
Right.
But it's a joint.
I mean, actually, let me show one example that will clarify the picture. And this example is actually, I'm going to show you how gradient descent fails even in a concave game. Okay, so, let's consider a two-player game. I guess I could do, this is the simplest example of gradient descent that fails that I know about. Okay, so two agents choosing scalar numbers, X, Y in R. So here the Nash equilibrium is 0, 0, right? So, so this is the Nash.
So they both receive payoff F?
Oh, it's a zero-sum game. I'm sorry. So one player, right? So one player wants to minimize that. The other, so I want to do, let's say, min over x, max over y, x times y. So the Nash equilibrium is this: if x plays 0, y cannot do anything. If y plays 0, x cannot do anything. If x plays any number, y can exploit x by playing plus or minus infinity, and vice versa. So the unique reasonable equilibrium is this one. The Nash equilibrium is this one. But here's how gradient descent fails. So in this example, the minimizing player is going to be doing gradient descent with some step size. And so the gradient of this of the x's utility is y, right? So the gradient of this objective with respect to x is just y, right? So this is the gradient of f with respect to x, and this guy wants to maximize. So they're going to be doing gradient ascent, and their gradient is this. So now basically what happens is like, like if you square this and add them up, what you get is that this and that squared is, I don't know, like this and that squared times 1 plus eta squared. So you see that these guys are going to spiral away. This is a very common behavior, right? So the equilibrium is here. You initialize the dynamics here. This is x naught, y naught. And what happens is you get this cycling behavior off to infinity. Now, if you're in a bounded domain, basically you're going to hit the boundary and you're going to be going on the boundary I think in some limiting cycle, okay? But you can modify this example where it's actually not even a limited cycle, but it's chaotic, like bona fide chaotic. Now, this being said, in the convex case, you can fix this. And the way you can fix this is you actually add a negative momentum term, which one way to define it is this, right? So like, I'm doing gradient descent, but I'm correcting by adding yesterday's gradient. So adding this correction actually will have the nice behavior that you're actually going to converge. But this fixing only works for the concave case. As my results suggested, in the non-concave case, there's no way to fix it to get to a fixed point.
Thank you. And actually, you answered my second question with the momentum. So
yeah. Okay. Cool.